Okay, Bismillah. Assalamualaikum and good morning. This is actually week 5. I need to correct the title of this slide here. Okay, I'm sorry we cannot have our class last week because I got some urgent matter, and even today actually I'm not feeling very well. But okay, we'll try to finish up this class. Okay, so today we're going to cover about a little bit about mesh diagram and vertical alignment and some calculations. Okay, first is about mesh diagram. This is actually part of your part of the survey actually. It's not really apa tu, in highway, but I think it's good for me to have a little bit of introduction about the mesh diagram in our course for your knowledge. So that this is not a calculation. I'm just going to explain it theoretically lah to you what mesh diagram is all about. So mesh diagram is a graphical representation of earthworks. For those who still haven't, for those who haven't accepted the link in your email, please accept it so that you can enter the class without having me to apa nama admit. If you don't accept it, I need to admit each and every one. Okay, each time you pop out in the class, I need to accept. Okay, so it's good for you to just accept the email link so that you can enter the class without being disturbing the class. I hope the class wrap. Okay, please inform your classmates. We are already in week 6 actually. Okay, I hope everybody is understands lah what they need to do. Mana tadi? Okay, it is a graphical representation of earthworks that need to be done. It's like you are plotting the amount of cut and fill for the earthworks lah, the amount of earthworks. So it is a continuous curve representing accumulated volume of earthwork plotted against the linear profile, okay, of the roadway. So mesh diagrams are prepared by highway engineers to assist in selecting alignment which minimize the earthwork to construct the facility. Okay, so on top of balancing between vertical and horizontal that I trust that many of you have started doing for your project, you can see that when you change the horizontal alignment, the vertical alignment will change. So you will get a different cut and fill amount for your alignment. So if you want to balance the amount of cut and fill, you need to change multiple times. Okay, if you're doing it manually, you need to do it multiple times lah, so that you can see that the total amount of cut and fill. Those cut and fill will be plotted on a diagram, okay, where the vertical axis here is actually the amount of cut and fill, and horizontal axis is your chainage. Okay, so the positive indicates excavation, and the positive side, negative side is in the fill, which is the embankment. Okay, so when you cut it, you're going to have cross sections like this. So this is an entirely fill segment of a cross section. So this is an entirely cut segment of a cross section, and this is both cut and fill is involved. So from here, you will get an area, the area here for every cross section. From that area, you will get, you will get the volume. calculate using maybe Simpson method or trapezoidal method, so you will get the volume. So this volume will be accumulated in this final column here. So cut and fill, cut and fill. All right, so you got positive here is cut and negative here is fill. 0 meaning that is the change between cut and fill. Okay. So but before you can actually estimate the volume, you must also know the shrinkage and swell factor, because different materials will have different shrinkage and compaction factor. For example, here rock fill. Okay, 1 meter cube of rock you excavate or you blast 1 meter cube of rock. Okay, and then in the loose state, it will be 1.75 meter cube. Okay, when you transport it, when you compact, it will become 1.4. So of course, it won't go back to the original state. So the same goes for sand, silt, and clay. Okay, for example here clay, 1 meter cube. You excavate, loose state becomes 1.5 meter cube. You compact it back, it becomes even denser than the original state. Okay, so this is where the shrinkage factor plays a role, where you use it to estimate the volume, the actual volume. Okay, so adjustments need to be made here. So when you plot, okay, so this diagram here is your mesh diagram. This is your profile. Okay, meaning that this is the natural terrain, and the red line here is your finer grade. Okay, your horizontal alignment. So you plot from here to here. You can see that all this is you need to remove, and this you need to fill. Here you need to remove. So the diagram will go up when it is cut. So it is accumulated, so it keeps on going up and up and up until it reaches the change point between cut and fill. From here, the diagram goes down, okay, because it is using up all these accumulated materials to fill this area over here. So it goes down, down, down until it reaches this point here, where it starting to cut again. Okay. So, okay, vertical mesh diagram correspond to the cumulative earthwork. Okay, within a cut, the curve rise from left to right. Within a fill, the curve falls from left to right. Okay. Lepas tu, the peak of a curve represent where the earthwork change from cut and fill. Okay, this one is what I mentioned just now lah. A valley low point on the curve represents a point where the earthwork change from fill to cut. Okay. So when a horizontal line intersects the curve at 2 or more points, the accumulated volumes at these points are equal. All right. So it doesn't mean that you just need you cut here and fill here, cut here and fill here. You can also from here going backwards. So these are the definitions from the definition that we use lah. The terminology. Free haul distance, meaning that this is a distance that you determine. Okay, actually this is being determined by the QS lah. Okay, the distance that you determine that you can move this amount of earth over here without additional money, meaning that you already have your machinery here. It is very short distance, so you can move this amount of earth without extra cost, meaning that the cost, of course there is going to be cost, but that cost is already is still within acceptable value. Overhaul is when you move this material to the other side. So it is over the free haul. meaning that this is also, this will cost you money, but it will cost you a lot more lah than the free haul. So the limit where you define that you still can accept some overhaul is the limit of the economic haul distance, this part. So for example, if you want to move excess material here, way across here, it is already beyond the limit of economic haul distance. So at this point, it is cheaper to waste the cart, okay, rather than to move it. So to move this material over here, way across the limit of economic haul, it is very expensive, and it is better for you just to leave the material here, and to fill the part over here, you get some other material from the front here. Okay, nearby borrow pit. All right. So borrow is it means material taken outside of the project, and waste material excavated material not used in the project. So this is going to be the waste, and this is going to be the borrow. Okay, the factors that determine the limit of economic haul, okay, the distance lah, mainly are determined by the machineries that you use. Okay, shorter distance we normally will move it with tractors. Okay, so it is about 500 feet. Okay, if you need to move it longer, you need to have different machineries, and the longest hauling distance is the trucks. So this is determined by the QS lah, how far they want to use it. But normally here it is mentioned it's about 3,000 or 4,000 feet. Okay, 3,000 to 4,000 feet. Okay. Actually, this is common lah. Tractor and trucks. Scraper, actually, I'm not sure. Scraper is a machine that it has a blade underneath the machine. Okay. That it scraps the surface of the filling area. The scraper. Okay. So next is the vertical alignment calculation. So you have two types, crest vertical curve and sag vertical curve. Okay, for crest vertical curve, it forms a crest, and sag, it forms a sagging area lah. So you have G1 and G2. So this is positive and negative. It also can positive, but it is still a crest. And it is negative, and it's still a crest here. The same goes for sag vertical curve, negative, negative, and positive. Okay, so now the calculations that we are going to go through, okay, in a moment, will cover crest vertical curve where it is negative and positive, and also here, negative and positive and negative, and negative and positive, meaning that there is a change of sign. Here there is no change of sign, you see. So this is positive, negative. So the calculation that we're going to go look at afterwards only covers where the curve has the change of sign, positive, negative, positive. All right, because we are using parabola properties. So G1 and G2. So G1 is the initial gradient. G2 is the final gradient. A is the absolute difference between G1 and G2. Okay, and the terminology that we use is the PVC, point of vertical curve. The first point is PVC, and then you have PVI, and then you have PVT. Here is delta angle. This is vertical alignment. And L is the length, the straight line length between PVC and PVT. It is not the length of the curving profile here. It is a straight line between PVC and PVT. PVI will always be in the middle between PVC and PVT. Thus, the distance of PVI will always L over 2 between PVC and also the same lah with PVT. Okay, PVI will always be in the middle. X is the distance we use, the term that we use for distance starting from PVC. So if you say that you want to measure the elevation of this curve at point 20, x is 20, meaning that from the starting point here is 20 meters to the right. Okay, so this is the parabolic equation that we're going to use. So this is the why we actually use when there is a change of sign, okay, between positive and negative, because we are using parabola punya properties. Okay, so y is the elevation at distance x. So this is the distance x. Y is the elevation of the beginning vertical curve in station. This point. Okay, going to the right. X is the distance from the beginning of the curve, I've mentioned just now. A, B, T. Okay, yeah. We'll go to A and B afterwards. C is the elevation of PVC. Okay, here. This is C. So what is A and B? A and B, when you differentiate the equation, the parabolic equation, so y equals ax squared plus bx plus c, you differentiate that term, it will become dy dx equals 2ax plus b. Okay, so you change the the terms here, so you get b equals dy dx, which is also equals as g1. Okay, so the initial curve is b. Okay, g1. And then you have the second derivative of the parabolic equation. So you differentiate again. Okay, so it becomes 2a. So 2a, you already know from the first term. So you input it here. So it becomes g2 minus g1 over L. Okay. So A is G2 minus G1 over 2L. Okay, you use these two terms over here. Okay, so A we know, B and C we already know. Right, so the relationships, this is the summary of relationships. You just remember this. B equals G1, A equals G2 minus G1 over 2L. C is the elevation at point PVC. Okay, here. Let I copy this already. Okay. So example 1. So you have a 200 meter equal tangent. Equal tangent meaning that the PVI will always be in the middle between PVC and PVT. Sorry lah, saya edit sikit. Okay. So the station, PVC here, the station is chainage 3 plus 700. Okay, chainage 3 kilometer, 3 kilometer and 700 meters. Or it is 3,700 meters from the starting point. Okay. The elevation is given 321 meters from mean sea level. So initial grade negative 3.5, final grade positive 0.5. So determine the elevation and stationing of PVI and PVT. Also determine the lowest point on the curve. Where is the lowest point? Okay. Because the curve is equotangent, PVI will be 100 meters from the PVC because it is always be in the middle. So the length of the curve is 200 meters. So PVI is 100 meter from PVC. And PVT will be 200 meter from PVC here. 100 and 100. Therefore, the stationing of PVI and PVT are 3 plus 800. So stationing lah. So this 3 plus 700 plus 100 meter here, it becomes 3 plus 800. And here is the chainage 3 plus 900. For the elevations of PVI and PVT, it is known that a negative 3.5 grade can be written as negative 0.035 meter per meter. Because PVI is 100 meter, the elevation from the we know the elevation here. So now we are going down. Okay. So the calculation will be 321. So we're starting here. Minus, because we are going down, 0.035 times the distance here. So you get 317.5 at this point. Okay, from this point, so you get the elevation of PVI lah. So now we are going up from PVI to PVT, so it's going to be plus here. And the gradient is 0.5, so it is 0.005 lah, because this is percent. Okay, 0.005 multiply with 100, and you plus with 317. So here, plus 0.5% times 100, you get the elevation of this point, elevation of PVT. So it is 318 meters. Okay. Okay, so it is explained here. It is, you know that the lowest point will occur when dy dx equals to 0. Okay, from that equation, you know B is negative 0.035 and A is equal to 0.0001. Okay, you know these values already. So we need to find where dy dx equals to 0. So you insert the value of A and B into dy dx. You got dy dx x equals to 175 meters. So the distance to the lowest point on the curve from the starting point, which is the PVC, is 175 meters. Somewhere here lah. Okay. So this gives the stationing of the low point at 3 plus 875 meters, where you add up here the 175 meters, you add here to 700, it becomes 3 plus 875 meters. Okay. For the elevation of the lowest point, the values A, B, C are substituted into the parabolic equation. You already know the x is 175 meters, the x of the lowest point. So now you put the value of x into the equation, you get the elevation of the lowest point. So it occurs at the elevation of 317.94. Okay. Second example, equotangent vertical curve is to be constructed between initial grade -2 and +1 final. Stationing of PVI is at chainage kilometer 11, elevation 420 over here. Due to a strait crossing the roadway, the elevation of the roadway at station 11 plus 71 must be 421.5 meter. Design the curve. Okay. The elevation of PVI and PVI, the chainage and elevation of PVI is given here. The percentage is already known. Okay. the initial grade and the final grade. But now we need to make sure that the point here, KNH 11 plus 71, must be at elevation 421.5 because there is a street crossing over here. Okay, so this is the same with your similar case with your project where you have existing roadway. So your new road must match, the elevation of your new road must match the elevation of the existing road, which is logical lah. You cannot construct your road higher or lower, okay, otherwise it cannot be connected lah. Okay. Okay, so design the curve. Okay, so the design problem is determining the length of the curve required to ensure that this station is at elevation 421.5. So we start here again with the parabolic equation. B, we know that it is negative 0.02. A is G1 over G2, G2 minus G1 over 2L. So we calculate, we don't know the L yet, okay? We know G1 and G2, so you know A is 0.015 over L. So you just put in the values for G1 and G2 first. So A will be in the terms of L. Okay. So note that C, elevation of PVC, will be equal to the elevation of PVI plus G minus multiply with 0.5 L. Okay, the elevation of C here, we are going up. We know the elevation here is 420. Therefore, the elevation of PVC is 420 plus negative 2% multiply with 0.5 L over here. 420 plus this, so the value of C will also be in terms of L. Okay. Now we know we have the value of A, B, and C, although it is still in the terms of L. Okay. Finally, the value of X to be used in equation 3.1 will be 0.5 plus 71 because the point of interest is 71 meters from PVI. Okay, you're already being told that the roadway will cross at chainage 11 plus 71, and this is chainage 11, okay, kilometer 11. So it is 71 meter away from PVI. Okay, so X will be 0.5 L, which is the distance from the starting point halfway to PVI. So that is 0.5 L and plus 71 meters, the distance between PVI to the point of interest over here. Okay, so substituting B equals negative 0.02, okay, the expressions for A, C, and X, and Y equals 421.5 meters, which is given here, over here. So you substitute everything, okay? This is the Y that is being given of the existing road, and you substitute all the terms that involves L here. So you solve for the value of L. So you'll get L equals 44.816, which is not feasible because we know that the point of interest is 71 meters beyond PVI. Okay, so the second value that you get using the quadratic punya formula is L equals 449.851 meters, which is the only feasible solution. So this means that the curve must be 449.851 meter long. Okay, so this is the value of L. 449.851 meters. Okay. So solving this quadratic equation, ini dah sudah tadi. Alright. So now the elevation of PVC, okay, you know the L, so you just substitute the value of L into the value of the equation of C here. So you get the elevation of PVC 424, okay, and the stationing is 11 plus 449 divided by 2 because L it is halfway from PVI. So you get the change of PVC. Elevation of PVT is elevation of PVI plus 0.5 G2. So you just put in the value of L and G2. So you get the elevation over here, 422.25. And the stationing of PVT, this is straightforward lah. 1100 here, 11 change 11 plus 0, which is the middle point, plus half of the L. So you get 224.926. Okay. And X equals 0.5 L plus 71. So that makes, that gives us apa tu? 295.926 meter from PVC. So this point here is 295.926 from PVC. Okay. So check the elevation so that you get the same value of X here, 295.926 using the equation lah. Okay, you check back, you get the Y is 421.5 meters. Therefore, the calculations are correct. Okay, so this is how we use the additional, bukan additional apa tu, the formulas, okay, to try to fit in our curve into an existing roadway. All right. So there are some other additional equations that we are going to use. Okay, so this is the figure. So the apa tu, terms that we are interested in are the value of Y, Ym, and Yf. But most of the time we are going to use either Y and Yf. Yf is the distance between the existing point on the curve to this imaginary line, okay, which is an offset value lah, okay, starting from G1. Okay, so if you extend this value of G1 up in the air until it reaches the point of PVT, the offset value, the distance between this PVT point on the alignment to this line is Yf. Okay, Y is the other distances along the point. Yf is for the distance at point PVT. Okay. X, again lah, X is the horizontal value. So the formula of Y is this, A over 200L multiplied with X squared. This is the value of Y. And other relationships, okay, you can use Ym, which is immediately under the point of PVI, and Yf here. Okay, Yf equals to AL over 200. And also importantly, most importantly, you need to know this lah, the relationships of K. K is the horizontal distance required to affect 1% change of the vertical curve. Curve is the length of the K is the length of the curve divided with the value of A, where A is the difference in the grade, the change of gradient. Okay, G1 minus G2 in percent, absolute, meaning that there is no negative. So this one, G1 minus G2. Okay. Okay, one last formula is the high and low point. Okay, high and low point is equals to G2 minus with modulus of G1, absolute value of G1. Okay, this is used to calculate the highest point or the lowest point. This is alternative way, additional formulas. All right, example 3. So you have a pipe with a diameter of 1 meter crossing a road. The location of the pipe is at chainage 11 plus 25. The center line, the center of the pipe here is chainage 11 plus 25. And the elevation of the center of the pipe here is 1091.6. Okay, it is so 1091.6 is in the middle of the pipe. The diameter of the pipe is 1 meter. So if you want to know the elevation on top of the pipe, you need to add 0.5 meter, which is half of the pipe's diameter, to the elevation of the center of the pipe. So 1091.6 meter here plus 0.5 is half of the pipe's diameter. You get the elevation on top of this pipe. Okay. The PVI of the vertical curve is at station 11,000. Okay, and the elevation ni tadi PVI. Okay, the elevation is 1095.2. This point here, which is on the air, in 1095.2. Vertical curve is 150 meter long. It's given here. The length is 150 meters and connects initial grade positive 1.2 and negative 1.08. So using offsets, so offsets value are the formulas that given here. So it is offset from the alignment here to this imaginary line of G1. So these are offsets. So using offsets, determine the depth below the surface of the curve to the top of the pipe. So we want to know how deep is the road, how deep is the pipe under the road. Okay. So determine the station of the highest point on the curve. So they need to know two things: the depth of the pipe and the highest station on the curve. So let's find the depth of the pipe first. So PVC is at station 10 plus 925, which is chainage 11,000 here minus half of the L. L is 150 meters, half of L is 75 meters. Okay, so the pipe is 100 meter or chainage 11 plus 25 minus chainage 10 plus 925 from the beginning of the PVC. So you know the distance of the pipe is 100 meter from PVC. Elevation of the PVC will be the elevation of PVI minus the drop of the grade. So we are starting here, elevation 1095.2. Because we want to go down to PVC, we minus, okay, we go down 75 meter, which is half of L, distance between here to here, multiply with 0.012, which is 1.2%. So you get the value of PVI, sorry, PVC, elevation of PVC is 1094.3 meters. So elevation over here is 1094.3. All right. Using this, the elevation of the initial tangent above the pipe. So starting from this point, PVC here, 1094.3, you plus 100 meter. 100 meter is the distance between PVC to the pipe and 1.2% of this gradient here. So it is like you are extending G1 over the pipe. Okay, so you're extending this line over the pipe. So the elevation here, 1094.3 plus the distance of 100 meter from this point to this pipe, multiply with the gradient. So the initial tangent above the pipe is 195.5 meters. So the point above the pipe here is 1095.5 meters. All right, so we use the offset formula above the pipe at x equals 100 meters. So now this is the formula of the offset. Y, bukan YF. This is Y, because we haven't reached PVT yet. Yeah, so we are using Y formula. So A is G2 minus G1 minus G2, and here is 200L. So you get the value of Y is 0.76 meters. So now you know the elevation of the point on air, okay, above the pipe, and you know the distance between that point to the surface of the road, which is 0.76 meter. So what you need to do is minus, you deduct 0.76 meters from 1095.5 meters. So you will get this minus this, you will get elevation 1094.74 meters. Saya tunjuk kat sini. Tengok sini lah. Okay. This minus this become, you get 1094.74 meters. Okay. So now you know the elevation on top of the pipe, like I mentioned, okay, earlier. Okay, you know the elevation center of the pipe. You know the elevation on top of the pipe. Okay, you plus apa nama 0.5. Okay, so center line 0.91.6 plus 0.5. You get the elevation on top of the pipe. So now you know the elevation here, you know the elevation here, you minus these two values, you will get 2.64 meters. So you know your road is 2.64 meters above the pipe. So why do we bother calculating this? It is because the loading of the traffic is dispersed in this way, in a triangular way. Okay? The lower the pipe gets, the less the effect of the traffic is going to be affecting the pipe. So you need to know whether the pipe is within a safe depth or not, so that the loading from the traffic will not affect, okay, the strength of the pipe. Okay. So to determine the highest point on the curve, we'll find K the value of K. So this is L over G1 minus G2. You got K value of 65.79. So now we use the high and low formula here. So you just put in the value of K multiplied with value of G1. So this gives you a value of X equals to 78.948. So the highest point on this curve occurs 78.948 meters from the starting point, PVC, here. So X, 78.948 meters. So this is the location of the highest point. Okay, tak apalah, dia tak kira elevation tu. Dia tanya distance saja. If you want to solve for the what is the elevation of the highest point, you need to substitute X equals this to the parabolic equation just now. Divided X equals to 0. Okay, ada ke? Alright. Okay. So next example. This is a slightly long example. We only have 2 more examples, but it is a little bit long to explain. So let's take 5-minute rest. 5-minute rest. So I'll get back to you at 11:05 lah. Okay, 5 minutes past 11. Thank you. Okay, let's continue our lecture. So example 4. So you need to construct a gradient. Existing tunnels need to be connected to a bridge. So you want to connect this tunnel over here with a bridge. So you need to develop a vertical alignment to connect the tunnel and bridge by determining the highest possible common design speed for the sag and the crest vertical curve. How to make sure that you can have the highest design speed for these two curves. So you have a sag curve over here and a crest curve over here. Compute the stationing of PVC, PVI, and PVT, and also suggest the design speed for the curve. So you are given the stationing of PVC as station 0. Stationing of the PVT is change 450 meters. Okay, so please note that this is PVCS, so starting point of the sag curve. And here is PVTC, the final point of the crest curve. The elevation of the tunnel floor is 100 meters, and the bridge deck elevation is 112.5 meters. So the difference of heights is 12.5 meters. The difference between the tunnel floor and the bridge deck is 12.5 meters. Okay, to complete this example, to solve this example, you have to use two tables. So this is the K value table for different design speed. Okay, so this table 3.2 here, is for crest vertical curves. So they have already calculated for a design speed, and this is the range of the design speed, 70 to 80. You get a range of K values. Okay, so this is the minimum, this is the maximum. So these values are being calculated considering the stopping side distance. Actually, we'll be covering this stopping side distance concept next week. So actually, this concept is a distance that is adequate for a vehicle to stop once the driver sees uh, a road, an object on the road. Okay, so by using this K value, a vehicle can stop as soon as they see an obstacle on the road. Okay, right. So for each design speed, you'll get a range of K values. So table 3.2 is for crest vertical curve, and table 3.3 is for sag vertical curves. Okay, from left to right. Okay, sag vertical curve, subscript S, and crest vertical curve have subscript C over here. Subscript F, S, and here is subscript C, indicating crest and sag. Okay, for the given information, it is known that initial gradient for the sag curve is 0, and the final gradient of the crest curve is also 0, because this part is flat and this part is also flat. So 0 over here, 0 over here. Okay. To obtain the highest possible design speed, we will want to use all of the horizontal distance available. Okay. This means that we will need to connect the curve such a way that PVT, okay, the last point of the sag curve, will be the first point or the PVC point of the crest curve. Okay, here. So PVT sag lies at the same point of PVC crest, 1 point over here, meaning that you only have a crest curve and vertical curve. There is no space between these two curves. Okay, the ending and starting lies at the same point. Okay, if this is the case, G2 of the sag curve is equal to G1 to the crest curve, meaning that the slope, the gradient will be one gradient lah. So this G2 for the sag curve is equal to G1 of the crest curve over here. Gradient is the same. Thus, because G1 for the sag curve and G2 for the crest curve equal to 0, it is flat, then the value of A for the crest sag is, the crest and the sag curve is one common value, 1A value. Okay, now we know the length between the first point and the last point is 140 meters. So you know that LS plus LC equals 450 meters. So here. So this is LS, length of sag curve, and this is the length of crest curve, where the total of both length is 450 meters. Okay. So total here is 150 meters. The elevation difference here is 12.5 meters. Okay. Okay. YFC plus YFS is 12.5 meters. So this is YFS. Okay. Please recall, if you extend this value G1 to the PVT point of this first curve, you will have YF sag curve. If you extend this line here of G2 until it reaches the point of PVT of this crest curve, you get the value of YFC. And the formula of YFC is this. YF equals AL over 200. Okay, Oh, ada sikit lagi. Also, the summation of the end of curve sag curve and beginning of offset. Ini yang tadilah 12.5 of the crest curve must be equal to 12.5 meters. Okay. YFS and YFC must be equal to 12.5 meters. So YF equals AL over 200, ALS over 200 plus ALC over 200, you'll get 12.5 meters. You rearrange these values, you get, and you plug in the value of LS plus LC equals 450 meters. You get the value of A equals to 5.556%. Okay, so now the problem becomes finding the K value that allow LS plus LC equals 450. So we know the formula of L is equal to Ka. So we can write, okay, LS plus LC in this form. So you change the value of L to K here. Ka. Ka for the sag curve and K for the crest curve, Ka for the crest curve equals 450 meters. You know the value of A is 5.556. So now you get the term Ks plus Kc equals 81. Okay. Um, to find the highest possible design speed, we use table 3.2 and 3.3. Okay. To get the value of Ks and Kc equals 81. So this is the value that we have calculated. So using this table, the first table, find the value of K for sag curve and find the value of K for crest curve that has a common design speed so that the total is 81. Okay, in reality, this is very difficult to get lah because this is an example. So you get an exact value. Okay, so looking at table 3.2 and 3.3, we see that the possible design speed is 80 kilometers per hour. Okay, tengok sini. So at 80 kilometers per hour, the K value is 49 for the crest vertical curve. And here, at 80 kilometers per hour, the sag vertical curve value, the K value is 32. So 32 plus 49, and the design speed is the same, 80 kilometers per hour, you get 81. Yeah. Okay, 49 plus 32, you will get 81. So you know the K value of sag curve is 32 and the K value for crest curve is 49. So you plug in the value of Ks and Kc into Ls and Lc, you get the value of Ls here as 177.78 meters and Lc equals to 272.222 meters. Okay, so the total of this should be 450 meters lah. Because the station of PVC is at channel 0, it is clear that PVI is 0 plus 88.889, which is half of this value. And PVT is 0 plus 177.78, which is this value, the length. So 0.0 plus 177.778. Okay. And PVI is at change 313.889. Dekat tengah-tengah kat sini. PVI kat sini at change 300 plus tadi tu. 313.889, okay, which is related with this LC pula. And PVT last point must be 450 lah, because the length you are given is 450 meters. So now the elevations, PVC and PVI is the same at 100 meters. Here, elevation here and here must be the same lah because it is flat. And here also must be the same. PVI crest and PVT crest must also be the same at the same elevation. 112.5. Finally, the elevation of PVT and PVC can be computed as using this YF formula, offset formula. So 100 is the value that you are given plus the offset value. So you get the elevation and of PVC and PVT is 104.94. Dahsyat betul. 11:21 baru masuk kelas je. Okay, so this diagram here summarizes the values that we have calculated. 177 divided by 2, and here 272 divided by 2. So from here you get the value of the chainages and the elevations for these points. Macam cepat pula saya explain. Rasa macam panjang ni ceritanya. Alright. Example 5. So example 5 is the same with example 4 in terms of problem. But in this problem, we want to have a separate space between PVC, between the sag curve and the crest curve. Okay, all the other values are the same, but now instead of having these 2 points at the same location, we want to separate the PVT of the sag curve and PVC of the crest curve. So determine the length of curve required to connect the bridge and tunnel while keeping the connecting grade as small as possible. We know that dia cakap sini, suppose a design speed of only 50 kilometers per hour is needed. So just now, the previous example, we used design speed of 80 kilometers per hour. Now they say reduce the design speed to 50 and provide a space between PVT here and PVC here. Reduce the design speed and separate these 2 points and have a G-con, the gradient of connecting space between the sag curve and the crest curve. Okay. It is known that the 450 meters separating the bridge and tunnel are more than enough. Okay, the space that you have, 450 meters, is more than enough, because if it can fit 80 kilometers per hour alignment, it surely can fit a 50 kilometer alignment, because this is lower. Okay, so example 3.7 showed that, okay, 80 kilometers per hour is possible. So 50 is not a problem. Therefore, to connect the bridge and tunnel and keep the connecting gradient as small as possible, we will place a constant gradient Sekejap, saya kena silentkan phone saya ni. Mana nak silent pun punya. Okay, 1 minute. Okay. We need to place a smallest gradient as possible between the sag and the crest curve. The elevation change will be the final offset of the sag and crest curve. Okay, tak apalah ni. Nanti kita tengok. Let G connecting be the grade of the constant grade section. So this means that G2 for the sag curve equals with G1 of the crest curve, and it must be equal to G connecting. Of course lah, you cannot have different gradients, otherwise you have other crest and sag curve between those two curves, isn't it? Okay, your road will become wavy. So you need to have one constant gradient. Okay, so now we know G1 and G2 for sag and crest curve equal to 0. Okay, this is the same. And for G connecting, the value of A, S, A crest, and the common A value here is the same lah. You only have one common A value. So now, the equation that will solve the vertical alignment for this problem will be ALS 200 for the set curve, and then you have ALC, sorry, for the crest curve here, and this term here is for the connecting part. Okay, here. So again, offset value using YF formula. The distance here from here is ALC 200 meter, and the distance ni pun sama lah sebenarnya kat sini value ni kan. From here to the point here, it is ALS over 200. Okay, because these 2 points are separated, you will have a third term, which is y equals A multiplied with 150 minus LS minus LC over 100. Okay, so this is A, and this is the percentage lah. Okay, how do you get this term? It's using this value. Okay, the gradient here is A percent, which is this one, A percent, A over 100. And A over 100 is equal, you can get by dividing vertical distance and horizontal distance. So we denote the vertical distance as y and horizontal distance as x here. So you rearrange these terms, you'll get y equals ax over 10. A is here, 100 is here, and x is 450 minus ls minus lc, because the distance between this point to this point is 450 meters. Here is the LC and here is LS. The space here is X. So X equals 450 meters minus this minus this. So you get Y. Okay, kat sini. And then you have the formula of L equals to KA. Okay, so L equals to AL over 200, and you change this value to you use these values lah, AL S over 200, and you plug in into this value over here. Okay, so we'll get A square times K over 200. Okay, so this is the explanation, the third term. So using L equals KA, you embed this value, L equals KA into this formula here. Okay, so now you have this L become KA. So A multiply with KA, you get A square, A square and K. Saya pun dah pelak cakap dah. Okay, A square and K, 200 for this term, and this is also same case lah. This is for the crest curve. And here also you replace this L with KA. You get this. Okay. So now you only have two things, K and A. A is common, right? Equals to 12.5 meters, because the difference is 12.5 meters. 12.5 meters here. This plus this plus this, 12.5 meters. Okay. Tengok sini. Ni. Satu ni kat atas. Okay. So now you know your design speed is 50 kilometers per hour. Dah beri 50 kilometers per hour. So for crest curve, 50 kilometers per hour is 10. The value of K is 10. And here, the value of K is 12. So 10 plus 12 is 22. Okay. Oh, ni tadi campur pun. So 10 and 12. So you put in the value of K into the previous formula here. You know the value of K sec berapa and KC how much. You put in those values and you get these terms. Okay. Simplify, it becomes this formula lah. Becomes parabolic equation. So you factor this, try get the value of A. So you get the A value for LS is 2.997 and A value for you get 2.997 or 37.92 because dia punya quadratic punya solution tu. So you choose 2.997 because this will result in a curve length exceeding 450 meters. So you use this 2.997, plug in into this L formula, you get LS equals 35.964 meters and LC equals 29.970 meters. Okay, dah tahu. And the length of the constant grade section will be 384.009. Why? Because 450 meters minus this, you'll get 384.066 meters. So this means that about 11.510 of the elevation difference will occur in the constant grade section. Okay, with the remainder of the elevation attributed to the final curve offset. So the distance here 11 point berapa something aja tadi. So this part and this part is about 1 meter je. Tak sampai 1 meter. So the constant gradient is 11 point berapa tadi? 510 meters. Wah, cepat pula. Dah habis. Okay. I hope you can understand lah. Boleh faham apa yang saya explain tu. So it is a matter of playing with the formulas. Okay, do you have any questions? I would like to okay. I would like to show you one thing.
Sorry, Doctor. Can you upload this PowerPoint slide to the Spectrum?
Yeah, sorry, I thought I've uploaded it, but it is not there, isn't it?
Yeah.
Sorry.
Last year lecture note.
Oh, you have the lights here. More or less the same, isn't it?
More or less the same, but there is a slight difference.
Okay, no problem. I will upload the most recent one lah.
Okay, thank you, Doctor.
Welcome.
Thank you, Doctor.
Belum habis, ada sikit lagi nak tunjuk. Relax dulu. Welcome. Okay, in your project design, there is a mistake in one of the cross-section example. Okay, in Chinese 50 here, I have written 0.12345 and this is the elevation for these points lah. 50, 55, 60, 70, 65 and 67.5. Okay, for channel 50. However, when I plot it, I think this is the one lah. Yeah. Okay, this is the other way around. This line is the other way around. So I got mixed up. This line should be like this. Okay, so I think this is the only mistake lah. Ini kawan ajar itu. Okay, sign. Kat ni. Sekejap je saya dah lupa Tak apalah. Boleh faham So this line should be the other way around. Ni saya salah lukis. Okay, no more questions I hope you have started with your project. Saya lupa. When is your due date for your project?
We should be asking you, Doctor.
Oh, I haven't stated
Haven't.
Okay. This is week 6. Week 10 lah.
Week 12.
Okay Is it possible?
Doctor, I have another question.
Mm.
To calculate the borrow earth, do we need to provide a mass hall diagram?
No, you just calculate the area from your graph, your vertical alignment graph.
Okay.
Okay,
Got it. Thank you, Doctor.
welcome. Okay, it is possible that between the two alignments that the options, the optional alignment that you have, one may not be you don't need super elevation transition, meaning that the curves can be too small in a way that the leading points overlaps with the tailing points. This can happen when your radius is very small. In those cases, what you need to do is try to increase the radius. Okay, if it still cannot, it's not possible, you can say that your road does not require super elevation transition. However, the submission that you, the selected, not selected lah, the one that you submit must include super elevation calculation. Okay, so the other one becomes like the alternative. But in the conclusion, you may say that you have submitted alternative 1. However, alternative 2 also is viable because of reason number 1, reason number 2, reason number 3. Okay, so you can say that actually the best alignment is alternative 2, but you submit alternative 1 because you need to show the super elevation development diagram. Okay. Okay, if there are no more questions, I think I'll end the class today. Thank you very much and have a nice day, everybody.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you.
Thank you.
Thank you, Doctor.
Thank you,
Thank you, Doctor.
Welcome.
Thank you, Doctor.
See you next week, Doctor.
Take
See
care.
you.
Stay
You too.
safe.
Stay safe, yeah, everybody.
Ya, Doctor. Submission tu lepas sikit.
Apa dia?
Week 12 lah, Doctor. Week 12.
Week 12.
Hmm.
Okay, week 12.